Hello, everyone. Welcome to the webinar. Today, I'm going to talk about OSNR and sensitivity and also dispersion. So the next one, just like an open question. OSNR stands for optical signal to noise ratio. And OSNR can be, as you can see, can be optimized by amplifying the noise, the signal, and reduce the noise level, such as in the equation shown. So usually we talk about receiver sensitivity in a short link and also in a short, low data rates. But in the long link, long haul system, especially when people use optical amplifier like a EDFA, OSNR becomes the way to estimate the performance of the link. And as you can see why, because the noise start to accumulate in the long fiber link, and it just overwhelms the receiver sensitivity. An example would be like, for instance, you have an ideal receiver with a sensitivity like a -40 dBm. And an inferior receiver with a sensitivity of -20 dBm. Any change of OSNR would impact A, which is the ideal receiver, much more than inferior receiver like a B. So in order to tell the performance of the receiver, and I suggest the absolute sensitivity of the receiver is an important figure of merit. And the next slide, I just show a very typical way to measure dispersion. The way that is, people put it, you can see if you would, the diagram, people put EDFA, sandwich the fiber together. This is very much like a classical type of setup. So both basically the purpose of this test, I was going to measure the dispersion penalty, right, by this EML laser. So going around, so you can see this line here is open nice. And then it becomes like this due to dispersion, right? So this eye is here without the fiber, or not even the EDFA. This one is here after the second EDFA. So very useful equation is that for 125 gigahertz at 1550 nanometer, the bandwidth is roughly around 12.5 gigahertz, or if you would like to see in wavelength, it's like a 0.1 of a nanometer. Assuming very similar signal distortion of fiber nonlinearity, you can calculate the signal to noise ratio by using the equation here, like 58 plus the input to the power input to the receiver, plus the noise figure of the amplifier, which is the sum of the receiver, minus the span. The span is how long you can reach, and minus also the 10 log of the number of amplitudes of amplifiers. So you can see here the span is roughly equal to 30 dB for receiver input 0 dBm, noise figure total 5 dB, and OSNR 20 dB, and with 2 amplifiers, right? So that's how to estimate signal to noise ratio in a system like this. So the following curve shows you how to plot the OSNR, right, with the sensitivity and by bit error rate, right? So this chart shows the bit error rate curve over different OSNR. You can see there are different OSNR level here by different curve here. So this data rate is 2.5 gigabits per second, PRBS 23rd. So this chart has no fiber, right? So the next one, I will have fiber. So basically, the ASE, the amplifier spontaneous emission noise is added in front of the receiver to simulate all those OSNRs. So the receiver sensitivity is equal to -29 for OSNR 16 dB for a 10 to the -10 bit error rate, right? So now remember this one. So this is without fiber, just purely OSNR. And the next page, I add the fiber there. So the fiber in 80 kilometers, and same amount, same number of curves for OSNR, just redo with the fiber. So basically, you can see the sensitivity degrade by 1 dB from -29 to -28 for the same amount of bit error rates, 10 to the -10. So what I try to show you is this curve. It's roughly a dB in between those two, right? So you can see those two curves are from no fiber to 80 kilometer fiber. Through different levels of OSNR, right, with the dispersion penalty here. So you can see it pretty linear. It's about a dB or so across. Okay, so this, I like to touch base a little bit on the dispersion penalty. I know most of all of you would know what dispersion penalty is. So it's basically the input pulses coming in through the fiber. It has two effects. One is the signal loss due to the insertion of the fiber, and also the spreading due to the dispersion penalty. Basically, the bandwidth of fiber decreases as the dispersion increases, right? Well, very quickly. And I put in this formula. For some of you interested in using the formula, you can use it as is. And it's a very good estimate to plot that out what happened for dispersion affecting the performance of your link. So I'm not going to go through one by one because it's too detailed. But basically, dispersion penalty is calculated, can be calculated by using those formula all the way through. Okay. You can plot out the curve like that by using all the information here, right? So I want to show you, this one is like a 0 picosecond per nanometer per kilometer. Dispersion is at 1310. You can really plot that out like that with the formula, same. So, and then this is one is more interest. That's the purpose why I do all these things. This one in blue is 10G. That's 10G curve. So this one is 25G curve. Plot again with the center fiber, operate at 1550 with the dispersion of 2 dB, and yeah, you can see the 17 picoseconds dispersion is pretty standard. And and then for the line width, again, people would use 0.1 to actually 0.3 of a nanometer line width. And I think typically it's about 0.2. So you can see 0.2 here intersecting the 25 gigabits per second is roughly on, theoretically, you can transmit this much, like a little bit more lower than 40 kilometers, right? And then, but it probably a little bit double for the 10G, right? You can see. Why I say this? Because, well, later on, I'm going to save this on the next slide. Now, here is like a rule of thumb on dispersion penalty. Pretty useful little things. Since because the allowable transmission distance, L, is inversely proportional to the data rate square, right? Remember, L is inversely proportional to data rate square. So the example I put in is like if L is 60 kilometers for 10 gigabits per second, then the length would be reduced to 10 kilometers for 25G and would be further reduced to 3 kilometers for 40G. So with a little simple equation like that, right? So 60 kilometer times 1 over the ratio of 25G over 10G, and then take a square, right? So 60 kilometer times 0.16 is equal to roughly 10 kilometers. Likewise, for the 40G, it's like 3 kilometers here, right? So, and the other one is 1-to-1 ratio for the transmitter distance is inversely proportional to the dispersion penalty. For instance, for length equal to 60 kilometer for dispersion of 2 dB, then the length would be reduced to 30 kilometers if for the dispersion penalty is 4 dB, right? So now let me go back to 1. You can notice the huge penalty on data, right? On increase of the data rates, right? It's a big difference. This is why now you can see for now all the high-speed link, namely above 10G, right? Like a 25G and then going to PAM and so forth. People are almost exclusively use 1310 nanometer, right? You can see right here why they want to do something like that, because they want to avoid the penalty. To keep the dispersion penalty to plus or minus 2 picoseconds per nanometer and kilometer, right? So for this type of design, we also have one. If you go to the website, it's available there. The wavelength for this transmitter is like in the 1310 range EML, like those 4 wavelengths in the WDM grid for the transmitter, and a pin plus a semiconductor optical amplifier inside the ROSA, okay, to operate at 25G NRZ. So the performance is respectable. You can see the transmitter power is a little bit higher than the non-SOA type of transceiver with extinction ratio 6 dB. Sensitivity can be achieved at about minus 28 dBm with the FET, right? So this one is with this system is pre-FET. By putting the FET, you have almost no error, right? So with the 80 kilometer, the power consumption is 6.5 watts, 0 to 70 degrees C. So this is still doable for 80 kilometer, 25 gigabits per second data rates. So we still have this luxury. But let me go back to here. So you can see that dispersion penalty is on 50/50. It's huge compared to what we do. Okay, so I just want to remind you as we go up in data rate, and there is going to be a problem to go long length or even the same length. So I think I give enough information. There's a lot of formula equations here, and I want to save a little time to ask you questions. But before I do that, are there any questions? Sentinel, are there any questions you can read out?
So far, we don't have any questions.
Okay, that's fine then. I have time to go through my last slide. So we've been doing this webinar for the last 2 months, one each week. Basically, 8 roughly 7 to 8 webinars. We would like to have feedback from all of you. Can you please send your feedback to info@vitextech.com about my questions here. One is that are the similar subject interesting to you? We want to have feedback. We want to have webinar to fit your need. Second one is what other topics you would like to see? We can do it non-transceiver as well. We can do fiber, we can do connector, we can do transceiver, mechanical, anything. But we need suggestions from you. Is this time slot convenience to you, or you would like to have different time slot? We would like to have some survey. And what else we can do to improve for better experience, your experience to attend this webinar, so you can get something out of it. So we definitely waiting for your feedback in order to evaluate our webinar. Also, for next week, we are having a company training next week, so we won't be able to do a webinar. The webinar will resume on the week after, the Thursday after. That will be on October the 15th. So yeah, and if there are, so we are waiting for your feedback, and I appreciate that as a presenter because I'm here. And yeah, Shantanu,
Yep.
Do you have anything to say to our colleagues?
Yeah, so thank you, Eric, for sharing your knowledge, and thank you everyone for joining. We hope you found it interesting. We'll be posting a recording of this webinar early next week. We would love to hear from you. So as Eric mentioned, our next webinar will be held the week after next. So once again, thanks everyone, and have a great rest of your week. Thank you.
Thank you.